10 Cosmic Lies. You have spent your entire life afraid of the wrong things. The black hole you picture as a hungry mouth. It does not hunt. It never did. The instant freeze you imagine waiting in open space. It would not touch you. Something else entirely would. Tonight, 13 things you believe about the universe are about to quietly fall apart. And what is waiting underneath every single one of them is far stranger and far gentler than you were ever told. If you enjoy our nighttime science journeys, remember to like and subscribe to Earth at Night. We highly encourage our community to discuss the topics in the comments and to react to each other. It is always more fun when we share our thoughts together. Now, let us begin. Tonight, you are going to lose 10 things you thought you knew about the universe. You will learn that the object you fear most in the cosmos does not pull the way you imagine. You will learn that the moment the universe began was not an explosion at all. You will learn why an astronaut exposed to open space would not freeze. You will meet a planet that has been quietly closer to you than Venus this entire time. And near the end of this journey, you will discover something stranger still. There is no center to the universe, which means in a very real and very strange way that you are standing in it right now. Chapter 1. Black holes do not suck. Picture it the way film and television have always shown it to you. A dark mouth turning slowly in space. A hungry spiral of light being pulled inward faster and faster as though the universe itself were being swallowed. It looks like a predator. It looks like something waiting. Let that image sit for a moment. Now, let it go. Because a black hole does not hunt. It does not reach out. It does not suck. The word suck implies a kind of active pulling, something different from ordinary gravity, a special hungry force. That is simply not what is happening. A black hole is not a cosmic vacuum cleaner. It is an object with mass, and mass makes gravity, and gravity behaves exactly the same way it always has everywhere in the universe. The only thing unusual about a black hole is how much mass has been folded into how small a space. Here is the simplest way to understand it. Escape velocity is the speed something needs to break free of a gravitational pull. On Earth, that speed is about 11 kilometers per second. Rockets are built to reach it. On the Sun, escape velocity is much higher because the Sun has far more mass. A black hole is simply an object where the escape velocity has climbed past the speed of light itself. Nothing, not even light, can move fast enough to leave once it has crossed that boundary. That boundary has a name. It is called the event horizon. Notice what that definition does not include. It does not say a black hole reaches out and grabs anything. It does not say the pull is stronger than gravity should allow at that distance. A black hole obeys the exact same law of gravity that keeps the moon in orbit around you tonight. The same law that keeps your own body resting gently against the surface you are lying on. The only difference is density, an almost unimaginable amount of matter compressed into a single point. Let us try something to make this feel real. Imagine just for a moment that the Sun vanished, and in its exact place, at the exact same mass, a black hole appeared instead. What would happen to Earth? Your instinct might say that everything would be pulled in, torn apart, dragged toward the new dark center of the solar system. But that instinct would be wrong. Earth would keep orbiting at exactly the same distance, at exactly the same speed, tracing the exact same path it traces now. Gravity would not have changed at all because the mass would not have changed at all. The only difference you would notice eventually and tragically is that the light and warmth would be gone. The sky would go dark and the temperature would fall. But you would not be pulled anywhere you are not already gently held. That is the strange gift of this correction. A black hole in the Sun's position would be no more dangerous gravitationally than the Sun already is. Distance is what protects you, the same distance that protects you now, not some special immunity to a stronger force. This holds true whether the black hole in question is small or almost incomprehensibly large. Some black holes form from the collapse of a single massive star and weigh only a handful of times more than the Sun itself. Others sit at the center of entire galaxies and weigh billions of times more than the Sun. Yet the rule never changes. Far enough away, the pull feels ordinary. It is only very close to the object itself where the strangeness begins. So what actually happens if something does fall in? This is where the language of hunger really breaks down. The event horizon is not a mouth. It is a mathematical boundary, a place where the geometry of space and time becomes so warped that no path leads back outward, not even for light. An object falling toward a black hole is not grabbed. It is following the curve of space-time itself, the same way a marble follows the curve of a bowl. There is no grip, no clutching, no decision being made by the black hole at all. Space is simply shaped in such a way that all paths past a certain point lead inward. What does tear an object apart is something called spaghettification, and yes, that is the actual scientific term astronomers use for it. Because gravity grows so much stronger over such a short distance near a black hole, the side of an object closest to it gets pulled far more strongly than the side farther away. That difference stretches the object into a long, thin strand, the way pulling gently on both ends of dough draws it into a thread. It is not a bite. It is a stretch caused entirely by the shape of space, not by any act of consumption. Here is a detail that overturns the predator image completely. Some of the most extreme black holes in the universe are not quietly eating. They are giving material back, and often more of it than they take in. Around certain supermassive black holes, matter that gets close but does not fall past the event horizon can be flung outward in enormous jets, streaming out at close to the speed of light for thousands of light years. These structures are called quasars, among the brightest objects known to exist. In many of these systems, more matter is ejected outward through these jets than ever crosses the horizon to begin with. The universe's most feared object is in a very real sense one of its great engines of ejection, not consumption. Think about what this means for how you have pictured the universe up until tonight. The thing you imagined as a hungry void turns out to be governed by the same quiet, patient rules that hold a coffee cup on a table or keep a satellite circling overhead. No malice, no hunger, just geometry, mass, and time behaving exactly as they always do, only pushed to an extreme most of us will never stand close enough to witness. It is a strange kind of relief, is it not? To learn that the darkest object in the cosmos is not reaching for you at all. It simply exists in its own quiet corner of space, following the same laws that let you rest peacefully right where you are. And if a black hole is not the monster you believed it to be, you might already be wondering what else you have been picturing incorrectly. As it turns out, the very story of how the universe began has been misunderstood in almost the same way. Not through malice, but through a name that never should have stuck in the first place. Chapter 2. The Big Bang was not an explosion. Close your eyes for a moment and picture the beginning of everything. Most of us were handed the same image somewhere along the way. A single point in empty darkness, a sudden flash, matter hurled outward into a waiting void, the way sparks fly from a struck match. It is a vivid picture. It is also almost entirely wrong. There was no waiting void. There was no single point sitting inside a larger emptiness. And there was no explosion in the way you have always imagined one. Let us start with the name itself, because the name is where the confusion began. The phrase Big Bang was not coined by an eager scientist trying to describe a beautiful new theory. It was coined in 1949 on a BBC radio broadcast by an astronomer named Fred Hoyle. Hoyle did not believe the theory. He preferred a rival idea called the steady-state model, in which the universe had always existed without any beginning at all. Historians still debate whether Hoyle meant the phrase mockingly or simply as a memorable shorthand. Either way, the name stuck. And Hoyle lost the scientific argument entirely. Within decades, the evidence for an expanding universe with a hot, dense origin became overwhelming. The theory he doubted became the foundation of modern cosmology, carried forward under a name invented by the man who doubted it most. It is worth pausing on how strange this history really is. A skeptic gives a rival theory its most famous nickname on live radio. The nickname survives long after the skeptic's own theory quietly fades from serious consideration. Scientists rarely choose their own vocabulary this way. Language tends to arrive first through public imagination and only later gets adopted formally. That is exactly what happened here. The strongest evidence supporting the expanding universe model did not arrive from a single dramatic discovery. It accumulated gradually across decades. In the 1920s, astronomer Edwin Hubble observed that distant galaxies were moving away from us, and that the farther away a galaxy sat, the faster it appeared to be receding. This was the first clue that space itself might be stretching rather than galaxies simply drifting through a static void. Decades later, in 1965, two radio astronomers named Arno Penzias and Robert Wilson detected a faint hiss of microwave radiation coming from every direction of the sky at once. At first, they assumed it was noise, interference from their equipment, even pigeon droppings on their antenna. It turned out to be something far more remarkable: the faint afterglow of the early universe itself, cooled over billions of years into the microwave range. This afterglow is now called the cosmic microwave background, and it remains one of the strongest confirmations that the universe once existed in a hot, dense state before expanding into the cooler, emptier place you see above you tonight. Now let us correct the deeper misunderstanding. The word bang suggests an explosion happening at a location, something detonating inside a pre-existing empty space. But there was no pre-existing empty space for anything to detonate into. Space itself did not exist yet in the way we experience it now. What actually happened is best described not as an explosion, but as a stretching. Space itself expanding and carrying everything within it outward together. Picture a balloon with dots painted across its surface before it is inflated. As the balloon expands, every dot moves farther away from every other dot. No dot is at the center of the balloon's surface. No dot is at the edge either, since the surface has no edge at all. Every dot would look out and see every other dot moving away from it, and every dot would be equally correct in thinking so. This is close to what happened with the early universe, except the stretching happened everywhere at once, not just across a surface, but through the fabric of space itself. This means there was no center to the Big Bang. Ask a cosmologist where it happened, and the honest answer is that it happened everywhere, simultaneously, including the exact spot where you are resting right now. The early universe was not a small, dense object sitting somewhere out in space. The early universe was everywhere that exists, only far smaller, far hotter, and far denser than it is tonight. There is another detail that quietly overturns the movie version of this event. Explosions make sound, but the early universe could not have made a single audible noise. Sound is a pressure wave. It requires particles close enough together to bump into one another and pass vibration along. In the earliest fractions of a second, there was no structure capable of carrying sound the way we understand it. The birth of everything was profoundly and completely silent. Now for the strangest part of the story, something that sounds like it should break the rules of physics entirely. In an unimaginably brief fraction of a second after the beginning, most cosmologists believe the universe underwent a period called inflation. During this period, space itself expanded by a factor of roughly 10 to the power of 26, a number so large it is difficult to hold in the mind at all. You may have learned that nothing can travel faster than light. That rule still holds, but it applies to objects moving through space, not to space itself. When space stretches, it can carry galaxies apart from one another faster than light, without any law of physics being broken. Because nothing is actually moving through space at that speed. Space itself is simply growing. It is worth saying plainly that inflation remains one of the most active areas of cosmological research today. The evidence supporting it is strong, but researchers continue refining exactly how and why it occurred. Sit with this reframing for a moment. Not an explosion into nothingness. Not a single point surrounded by waiting empty space. Instead, an expansion of existence itself happening everywhere at once in complete silence, followed by an almost incomprehensible stretching that carried the seeds of every galaxy you have ever looked up at into position. It can help to try to feel the scale of that inflationary moment rather than simply hear the number. Imagine something the size of a single grain of sand growing in a fraction of a second to something larger than the entire observable universe is today. That comparison still barely does it justice, but it hints at just how far our ordinary intuitions about size and speed break down at the very beginning of time. None of this happened because space was pushed by any force in the way a hand pushes a ball. It happened because the underlying fabric of space carried a kind of energy that caused it to expand on its own, rapidly, uniformly, everywhere. There is something quietly beautiful in this correction. The universe did not begin as a small, violent event happening far away from you. It began everywhere, which means it began here too, in whatever room you are resting in tonight. You are not separate from that beginning. You are made of the same stretching fabric that has been expanding gently for billions of years. If the beginning of everything turned out to be gentler and stranger than you imagined, you might start wondering what other assumptions about the physical world deserve a second look. Here is one that feels almost too obvious to question. The simple idea that space itself is cold. As it turns out, even that familiar assumption is not quite telling the whole story. Chapter 3. Space will not freeze you instantly. You have seen the scene before. A helmet cracks. A visor frosts over in an instant. A body drifts and stiffens as ice crystals bloom across exposed skin within seconds. It is one of the most enduring images science fiction has ever given us. And it is almost completely false. To understand why, we need to ask a very simple question that most of us have never actually stopped to consider. What does temperature really mean? Temperature is not some invisible substance that exists on its own. Temperature is a measurement of motion. Specifically, it measures how fast the particles within a substance are vibrating and colliding with one another. A hot cup of tea has fast-moving, energetic molecules. A block of ice has slow, sluggish molecules. Heat is not a thing that exists independently. It is simply a description of how much particles are moving. Here is where space becomes strange. In order for temperature to transfer between two things, there usually needs to be contact, or at least a medium like air or water that particles can move through to carry that energy away. But the vacuum of space contains almost no particles at all. In a near-perfect vacuum, the very concept of temperature becomes difficult to define in the way we experience it on Earth. There is nothing nearby dense enough to rapidly steal your warmth away the way icy water would. This is the opposite of what most people assume. Space is not aggressively cold in the way a freezer is cold. It is empty in a way that makes the normal rules of heat transfer barely apply at all. So, if an astronaut were suddenly exposed to open space without a suit, what would actually happen? Not instant freezing. The real danger is something else entirely. The human body loses heat to a vacuum only through radiation. The same slow process by which a campfire warms your face from a distance without touching you. Radiative heat loss is remarkably slow. Roughly 100 watts leave the body this way under normal conditions, comparable to a single incandescent light bulb. At that rate, a person would not freeze solid in seconds. It would take a very long time for the body to cool significantly through radiation alone. The true danger is asphyxiation, not frost. Without oxygen and without the pressure, the lungs and blood depend on a person exposed to vacuum would lose useful consciousness in roughly 15 seconds. Long before any meaningful drop in body temperature could occur. There are other real dangers too. Gases dissolved in bodily fluids can begin to expand as pressure drops. This is closer to the effects of sudden decompression seen in scuba diving accidents than anything resembling a freezer. None of this is gentle or safe. It is simply a very different danger than the one Hollywood has trained us to imagine. There is a detail here that makes the frozen astronaut myth even stranger once you consider it closely. Spacecraft in orbit experience some of the most dramatic temperature swings imaginable, not because space itself is uniformly cold, but because there is so little atmosphere to even out temperature at all. The sunlit side of an orbiting spacecraft can reach roughly 250 degrees Fahrenheit, hot enough to be genuinely dangerous. Meanwhile, the shadowed side facing away from the sun can plunge to roughly negative 250 degrees Fahrenheit at the very same moment. A swing of about 500 degrees between one side of a spacecraft and the other, simultaneously. This alone should tell you that describing space simply as cold is far too simple a label. Space is not one temperature. It is an environment where the absence of a medium makes heat behave in ways nothing on Earth prepares you for. It is worth pausing on why this particular myth took hold so firmly in the first place. Fiction needed something visually dramatic and instantly readable to an audience. A frozen visor communicates danger in half a second of screen time. The slower, truer story of asphyxiation and radiative cooling does not translate as easily into a single striking image. So filmmakers reached for frost because frost reads instantly as cold, and cold reads instantly as space. The myth was never really about physics. It was about storytelling shorthand that slowly hardened into something audiences began treating as fact. It is also worth noting that human bodies are surprisingly good at insulating themselves for short periods, even in extreme environments. Skin and fat provide a meaningful barrier against radiative heat loss, even without a suit. Historical incidents of accidental depressurization in high-altitude testing, and even a small number of documented space program accidents, have given researchers real data here. In every known case, oxygen deprivation was the immediate danger, not freezing. Survivors of brief accidental exposure describe swelling and the sensation of carbonation on the tongue from dissolved gases expanding, not cold. The body has time before temperature becomes the primary threat, just not very much time before oxygen becomes one. If you want to know what genuine cold actually looks like in the universe, you have to travel much farther than low Earth orbit. Roughly 5,000 light-years away sits a strange structure called the Boomerang Nebula, a cloud of gas being expelled by a dying star at extraordinary speed. As that gas expands outward, it cools dramatically, bringing the nebula down to a temperature of roughly 1 Kelvin. just barely above absolute zero itself. This makes the Boomerang Nebula colder than the faint background glow left over from the birth of the universe. Colder even than the empty vacuum of space between stars. It remains the coldest natural place scientists have ever measured anywhere in the observable universe. Scientists studying the Boomerang Nebula believe its extreme chill comes from an unusually rapid rate of gas expansion. Material rushing outward at roughly 164 kilometers per second in every direction from the dying star at its heart. Rapid expansion of a gas naturally causes it to cool. The same principle behind an aerosol can feeling cold to the touch as pressurized gas rushes out of the nozzle, only on a scale involving an entire dying star system rather than a small canister. Sit with that contrast for a moment. The vacuum surrounding you as you look up at the night sky is not reliably cold in the dramatic, instant-acting way fiction has always promised. Yet somewhere out there in the depths of space sits a nebula colder than anything you could ever encounter naturally on Earth. The universe does not deal in simple labels like hot or cold applied evenly everywhere. It deals in extremes, distributed unevenly, shaped by density, motion, and distance rather than any single uniform temperature waiting to greet you the moment you leave the atmosphere. You have now corrected 3 of the most common fears people carry about the universe. That black holes hunt. That the beginning of everything was a violent explosion into nothing. That the vacuum of space would freeze you instantly. Each fear traced back to the same root cause, applying an intuition built for ordinary human experience to a scale where that intuition simply does not hold. Now the tone of this journey gently shifts, from the sharp, visceral corrections of the opening chapters into something quieter, starting with a color you have been looking at your entire life without ever truly seeing it correctly. Chapter 4. The sun has never been yellow. After the intensity of the last 3 corrections, let this chapter feel like a slow exhale, a quieter myth, a gentler unraveling. Close your eyes and picture the sun the way you likely drew it as a child. A warm, cheerful circle, bright yellow against a blue sky. It is one of the most universal images we carry, taught to us before we could even properly hold a crayon. And yet the sun has never actually been yellow at all. To understand why, we need to talk about light itself and the way our own atmosphere quietly reshapes it before it ever reaches your eyes. Sunlight leaving the sun is made of every color combined, every wavelength blended together into something that would actually appear pure white if you could view it without any atmosphere in the way. But sunlight does not reach you directly and cleanly. It has to pass through miles of air first, full of tiny molecules of nitrogen and oxygen. Here is where a phenomenon called Rayleigh scattering enters the story. Shorter wavelengths of light, the blues and violets, scatter far more easily off these small air molecules than longer wavelengths like reds and oranges do. As sunlight travels through the atmosphere, the blue light gets knocked around in every direction, filling the entire sky with that familiar blue color you see stretching from horizon to horizon. Meanwhile, the direct beam of light, traveling straight from the sun to your eye, has lost some of that blue along the way, leaving it looking shifted toward warmer tones. This effect grows dramatically stronger at sunrise and sunset, when sunlight has to travel through a much longer stretch of atmosphere at a low angle, scattering away even more blue and green light and leaving behind the deep oranges and reds that make sunsets so beautiful. So the yellow-orange glow you have always associated with the sun is not a property of the sun itself. It is a property of Earth's atmosphere, borrowing and bending sunlight on its way down to you. We do not have to take this on faith alone. Astronauts who have traveled beyond the atmosphere consistently describe the sun as appearing blinding white, not yellow at all. Without miles of scattering air in the way, there is nothing left to filter out the blue light and shift the remaining color toward warm tones. The sun simply appears as what it actually is: a brilliant white light containing every visible color blended together at once. There is a simple experiment you can imagine to feel this effect for yourself. Picture standing on a mountain at sunrise, watching the sky lighten. High overhead, the sky already glows a rich, deep blue even before the sun itself has cleared the horizon. That color is scattered light arriving from a sun that has not technically risen for you yet. Then, as the sun itself finally clears the horizon, its disk appears deep orange or red, precisely because you are viewing it through the thickest possible slice of atmosphere at that low angle. By midday, when the sun sits high overhead and sunlight only has to pass through a comparatively thin layer of atmosphere directly above you, that same disk appears far closer to a pale white or soft yellow, because far less blue has been scattered away along the shorter path. The sun itself has not changed even slightly between sunrise and noon. Only the thickness and angle of the air standing between you and it has changed. And that alone accounts for the entire dramatic shift in apparent color you witness every single day without ever questioning it. This raises a fair question. If the sun is not yellow, why do astronomers still call it a yellow dwarf star? The answer is that this classification has almost nothing to do with visual appearance at all. Stars are grouped into categories based primarily on their surface temperature, and the category historically labeled yellow simply describes a temperature range, not a color you would actually see with your own eyes. It is an old naming convention from early astronomy that has stuck around long after our instruments became precise enough to reveal the true visual color involved. To really appreciate where the sun sits on the scale of stellar colors, it helps to meet its neighbors. Consider Sirius, the brightest star in our night sky, burning at a surface temperature of roughly 10,000 Kelvin. Sirius radiates a crisp blue-white light, distinctly cooler in tone than what you might expect from something so hot and bright. Now consider Betelgeuse, the massive red giant marking the shoulder of the constellation Orion. Betelgeuse burns at a comparatively cool surface temperature of roughly 3,400 Kelvin and glows with a deep, visible red. Our own sun sits comfortably in between these extremes, hot enough to avoid the deep red of Betelgeuse, cool enough to avoid the piercing blue of Sirius, landing instead on a true balanced white. Color in stars follows temperature with remarkable consistency across the universe. Cooler stars glow red, hotter stars glow blue, and stars in the middle range like our own glow in a pure white that our atmosphere quietly disguises as yellow every single day. It is worth noting that Rayleigh scattering also explains why the sky itself is blue rather than violet, even though violet light scatters even more easily than blue light does. Two reasons explain this small additional detail. The sun emits somewhat less violet light to begin with, compared to blue, and human eyes are simply less sensitive to violet wavelengths than to blue ones. Combine a slightly weaker violet signal with eyes that respond to it more faintly, and the sky settles into the blue you recognize, rather than a deeper violet that physics alone might otherwise predict. There is one more layer of nuance worth including here, since accuracy matters even in a gentle correction like this one. If you were to measure the exact wavelength where the sun emits the most energy of all, it actually falls closest to the green portion of the visible spectrum. This does not mean the sun is secretly green. Human eyes combined with the full spectrum of light the sun emits blend everything together into a perception of pure white rather than any single hue standing out. Color perception is a strange partnership between physics and biology, and in this case that partnership produces white, not yellow, and not green either. There is something quietly moving about this particular correction. A small piece of childhood innocence gently replaced, not by disappointment, but by something closer to wonder. The sun you have looked at your entire life turns out to be more brilliant and more purely luminous than you ever gave it credit for. Its familiar yellow warmth was never really its own. It was a gift borrowed from the very air you breathe, bent gently on its way down to greet you. If color can be quietly reshaped by the space between a source and your senses, you might start to wonder what else gets distorted along the way. Sound travels through very different rules than light does, and in the vast emptiness between stars, those rules reveal something almost impossible to imagine from where you are resting right now. Chapter 5. The universe is almost completely silent. For a channel built around rest, this might be the most fitting correction of the entire night. Let yourself sink a little deeper into this one. You have heard it in countless films: starships roaring past, explosions thundering across the void, laser blasts cracking through open space like thunderclaps. It feels natural, it feels dramatic, and it is almost entirely false. The truth is quieter than anything Hollywood has ever shown you. The vast majority of the universe carries no sound at all. Consider how strange this is when you first really sit with it. On Earth, silence is rare and often uncomfortable. We fill quiet rooms with music. We reach for background noise while falling asleep. Complete silence can feel almost unsettling to a species that evolved surrounded by wind and rustling leaves and the calls of other animals. Yet true silence is not the exception in the universe. It is overwhelmingly the rule. Nearly the entire volume of existence sits in a stillness deeper than any soundproofed room ever built on Earth. To understand why, we return to a simple definition. What is sound really made of? Sound is a mechanical wave, a pattern of compression and release traveling through particles that are close enough together to bump into one another and pass that vibration along. Air works well for this. Water works even better. Solid materials like metal or stone can carry sound faster still. But a vacuum contains almost no particles at all, nothing close enough together to bump into anything. Without a medium, there is nothing for a vibration to travel through. And so, in true empty space, sound simply cannot exist. Not because it is too faint to hear, but because the physical mechanism required to create it is not present at all. It helps to compare this to something familiar. On the sun, molten plasma churns violently, and enormous eruptions called solar flares release energy equivalent to millions of hydrogen bombs. If you could somehow survive close enough to witness this directly, you still would not hear it. The corona surrounding the sun is itself an extremely thin and rarefied plasma, far too sparse in most regions to carry sound effectively across any meaningful distance. Even the most violent events our own star produces unfold in a silence that would astonish anyone expecting the thunder Hollywood has trained us to imagine. This same rule extends outward across nearly the entire volume of the observable universe. Supernovae, colliding galaxies, the formation of new stars inside vast clouds of dust. All of it occurs without a single audible sound reaching any observer positioned in the surrounding emptiness. This makes one particular piece of 1979 film marketing genuinely remarkable. The tagline for the film Alien famously read, "In space, no one can hear you scream." It was written as a chilling piece of horror marketing, and by pure coincidence, it also happens to be accurate physics. Meanwhile, countless other space films fill their soundtracks with roaring engines and explosive blasts precisely because true silence does not translate well to an audience expecting cinematic excitement. Real space combat and real starship engines operating in a vacuum would produce nothing you could hear at all. Not a hum, not a roar, not even a faint hiss. Just complete and total silence surrounding an event that might otherwise look tremendously violent to witness. Now, here is a detail that seems to complicate this picture at first before deepening it further. In 2022, NASA released what became known as the sound of a black hole, a recording that spread rapidly across the internet, specifically because it sounded genuinely eerie and unsettling. This recording came from the Perseus galaxy cluster, a region containing an enormous amount of hot gas surrounding a supermassive black hole at its center. Unlike the empty vacuum between stars, this gas cluster actually does contain enough particle density for real pressure waves to travel through it. Astronomers detected these pressure waves using an instrument called the Chandra X-ray Observatory. The waves themselves existed far below the range of human hearing, roughly 57 octaves below middle C, far too low and far too slow for any ear to detect directly. Scientists took this genuine astronomical signal and scaled it upward by roughly 288 quadrillion times its original frequency, bringing it into a range human ears could finally perceive. It is worth being precise about what this recording actually represents, because it could easily be misunderstood as contradicting everything just explained. This was not sound crossing the empty vacuum of space the way scenes in science fiction films portray it. It was a real physical pressure wave, traveling through unusually dense gas surrounding a black hole, mathematically translated and pitched upward until human ears could register it. The true vacuum between stars and galaxies remains genuinely silent. This recording simply reveals that dense gas clouds around extreme objects can behave differently from the emptiness found in most of the universe. This distinction matters more broadly than a single viral recording. Astronomers have used similar sonification techniques on many different kinds of data over the years, turning light curves from distant stars into musical tones, turning the structure of galaxies into layered soundscapes, turning gravitational wave detections from colliding black holes into short, audible chirps. None of these techniques capture sound traveling through space the way your ears experience sound on Earth. They are translations, a way of letting human senses experience data that was never acoustic to begin with, useful for research, useful for public understanding, but never a contradiction of the underlying silence of true vacuum. There is something deeply calming about sitting with the true silence of most of the cosmos. No roaring engines, no explosive booms, no screaming winds. Only an overwhelming stillness stretching across nearly the entire volume of existence, broken only in the rare pockets where enough matter has gathered densely enough to carry a vibration at all. If you are listening to this while drifting towards sleep, let that stillness settle over you, the way it settles over most of the universe itself. Almost everything out there rests in a silence deeper than anything you will ever experience here on Earth. Even on our own quiet planet, true silence is nearly impossible to find. There is always some faint hum, wind moving through trees, distant traffic, the sound of your own breathing and heartbeat if the room grows quiet enough. Out among the stars there is no wind to hum and no air to carry even the faintest whisper of it. Only vast reaches of cold, empty distance, stretching between one lit point and the next, utterly still, utterly silent, patiently waiting for nothing at all. From true cosmic silence, let us shift now to a very different kind of myth. One rooted not in physics at all, but in a piece of folklore that managed to survive for centuries before anyone actually left the ground to check whether it was true. Chapter 6. The Great Wall cannot be seen from space. This next correction has a slightly different flavor than the ones before it. It is not really about physics at all. It is about how a single, confident guess can travel for centuries. Repeated so often, it eventually gets mistaken for verified fact. Almost everyone has heard the claim at some point in their life. The Great Wall of China is the only human-made structure visible from space. It sounds impressive. It sounds plausible given how long the wall stretches across the landscape. It also happens to be false, and the story of how this myth began is almost more interesting than the correction itself. The claim did not originate from any astronaut or any space program at all. It traces back all the way to 1754, written by an English antiquarian named William Stukely. Stukely speculated in his own writing that the Great Wall might be visible from the moon. This was more than 2 centuries before any human being had traveled to space at all, let alone the moon itself. There was no way for Stukely to test this claim in any way. It was pure speculation, an educated guess about scale dressed up in confident language. Yet somehow that guess survived, passed along through books and casual conversation for generation after generation, until it hardened into something people simply accepted as established fact without ever questioning where it originally came from. It helps to understand just how the myth grew from a single speculative sentence into something taught as established fact in classrooms around the world. Ripley's, believe it or not, helped popularize the claim in the early 20th century, presenting it as a marvel of human engineering rather than an unverified guess. Once a claim like this appears in a widely read publication, it tends to take on a life of its own, repeated by teachers who trusted their own textbooks, repeated by textbook authors who trusted earlier sources, each retelling adding a small additional layer of borrowed authority without anyone actually testing the claim directly. By the time human beings finally reached orbit in the 1960s, the myth had already been circulating confidently for roughly 2 centuries, waiting quietly for someone to finally look down and check. So what do people who have actually been to space say about this? China's first astronaut, Yang Liwei, traveled to orbit in 2003 aboard the Shenzhou 5 spacecraft, orbiting Earth 14 times over the course of his mission. When asked directly whether he had seen the Great Wall from orbit, his answer was simple and direct. He had not seen it at all. This response actually caused some public disappointment back in China at the time, given how widely the myth had been taught in schools. Yang Liwei is far from alone in this observation. Numerous other astronauts from multiple national space programs have echoed the same conclusion across decades of spaceflight. Under normal viewing conditions with the unaided eye, the wall simply does not stand out clearly from low Earth orbit. Why would something so famously long remain so difficult to see from above? The answer comes down to a factor most people never consider when picturing visibility from orbit: contrast, not length. The Great Wall averages only around 6 to 7 meters wide in most sections, and it is largely constructed from materials like stone and packed earth that closely match the color and texture of the surrounding terrain it winds through. From hundreds of kilometers above the surface, a structure needs strong contrast against its background to stand out visually. Not simply impressive total length. Highways, airport runways, and large-scale agricultural field patterns are all considerably easier to spot from orbit, specifically because they contrast sharply against the landscape around them. Even though none of these structures come anywhere close to matching the wall in total length. The Three Gorges Dam, a single massive concrete structure spanning the Yangtze River, is considerably easier to identify from orbit than the much longer but narrower and more naturally camouflaged wall ever is. To put this in perspective, consider how city lights transform the view of Earth at night. From orbit after sunset, entire coastlines and metropolitan regions blaze with light in patterns instantly recognizable to anyone familiar with a map. A structure like the Great Wall, built from stone and earth, produces no light of its own and blends into surrounding hills and terrain during the day. It should not be surprising that a modern illuminated city is easier to identify from space than an ancient fortification built centuries before electricity existed at all. Contrast, in every sense of the word, decides what gets noticed from orbit far more than raw scale alone ever could. There is an important nuance worth preserving here, rather than overcorrecting into an equally simple but slightly inaccurate opposite claim. Under specific conditions, using telephoto lenses and significant magnification, astronauts and orbital cameras have captured images that arguably show faint traces of the wall in certain sections. This is meaningfully different from unaided naked eye visibility, though. The corrected claim here is not that the wall is utterly undetectable under any circumstance whatsoever using any equipment ever devised. The corrected claim is specifically that it is not visible to the unaided human eye the way the popular myth has always insisted, a distinction that matters a great deal once you start comparing specific testimonies against specific viewing conditions. It is worth remembering that this same confusion between the Great Wall and the asteroid belt appears elsewhere in popular imagination too. Both places are often pictured as far more crowded and visually dramatic than they actually are once examined closely, a detail worth holding on to as this journey moves further outward into the solar system later tonight. There is something almost comforting about a myth like this one compared to the sharper corrections earlier in this episode. No fear here, no dread. Just a quiet reminder that confident-sounding claims can travel remarkably far before anyone with first-hand experience finally steps forward to correct them. A guess from 1754 managed to outlive its original author by more than 2 centuries, carried forward by nothing more than repetition and the comforting shape of a good story. It is a useful habit to carry forward from this chapter into everything else you learn for the rest of your life. Not skepticism for its own sake, simply a gentle curiosity about where a confident-sounding claim actually came from before accepting it fully. Sometimes a claim traces back to careful measurement and rigorous testing, and sometimes it traces back to a single antiquarian in 1754 making an educated guess about the moon. If a structure this famous could be misunderstood for centuries simply because no one had checked, yet you might wonder what other beloved cultural stories about space deserve the same kind of gentle scrutiny. As it happens, one of the most famous album covers in music history carries a similar kind of quiet misunderstanding built directly into its name. Chapter 7. There is no dark side of the moon. Few phrases in modern culture carry as much poetic weight as this one, anchored forever to one of the most beloved albums ever recorded. But the phrase itself carries a quiet misunderstanding built directly into its name. There is no permanently dark side of the moon at all. Let us start with why the moon shows us the same face every single night regardless of the date or season. This is not a coincidence. It is the direct result of a phenomenon called tidal locking. Over billions of years, Earth's gravity gradually slowed the moon's rotation until its rotational period matched its orbital period exactly, both cycles lasting roughly 27.3 days. Because these two cycles are perfectly matched, the same lunar hemisphere always faces toward Earth, while the opposite hemisphere always faces away. This is not some rare cosmic coincidence unique to our own moon either. Tidal locking appears throughout the solar system. Many moons orbiting Jupiter and Saturn show the same behavior toward their host planets. It is simply the natural long-term outcome of gravity acting on two orbiting bodies over enormous stretches of time. It can help to picture this process the way you might picture two dancers slowly settling into step with one another over a very long song. Early in the moon's history, it likely rotated much faster relative to its orbit around Earth, just as any newly formed body might. Earth's gravity acted on the slight bulge and unevenness of the young moon's shape, creating a gentle drag that gradually slowed its spin. Over hundreds of millions of years, this drag brought the moon's rotation into an exact match with its orbit, locking one face permanently toward us and the other permanently away. A slow, patient dance stretched across an almost unimaginable length of time. Now here is where the phrase dark side becomes genuinely misleading. The far side of the moon receives exactly the same amount of sunlight over the course of a lunar cycle as the near side we always see. As the moon rotates in its tidally locked orbit, sunlight sweeps across every part of its surface in turn, including the hemisphere permanently hidden from Earth's view. The far side experiences its own full cycle of lunar day and lunar night, just as bright and just as dark in turn as the side you have looked up at your entire life. The word dark in this famous phrase was never actually describing sunlight at all. The 1973 album that made this phrase so iconic used dark side as a metaphor, pointing toward hidden aspects of the human mind. Madness, isolation, the parts of ourselves we rarely show to others. It was poetry about psychology dressed in the language of astronomy, never intended as a literal scientific claim about which lunar hemisphere receives sunlight. Yet somewhere along the way, listeners began treating the phrase as though it were describing an astronomical fact rather than a metaphorical one, and the misunderstanding has quietly persisted ever since. So, if the far side is not literally dark, what is actually different about it? Quite a lot, as it turns out, just not in terms of light. Humanity's first real glimpse of the lunar far side came in 1959 when the Soviet spacecraft Luna 3 captured the first photographs of this hidden hemisphere. What those images revealed surprised scientists at the time. The far side looks strikingly different from the near side we have always known. The near side of the moon is covered in large dark patches called maria, ancient basins that were once flooded with molten lava billions of years ago, before cooling into the smooth, dark plains you can still see with your own eyes tonight. The far side, by contrast, is almost entirely covered in pale, heavily cratered highlands, with very little evidence of the same widespread lava flooding seen on the near side. Scientists are still refining their understanding of exactly why these two hemispheres developed so differently. Leading theories point toward differences in crust thickness between the two sides, possibly influenced by Earth's own gravitational pull shaping the moon's interior asymmetrically over billions of years, or by an ancient impact early in the moon's history. Whatever the ultimate cause, the result is a genuinely striking asymmetry. Two hemispheres of the same small world looking almost like two entirely different places, not because of light and dark at all, but because of geology written across billions of years of separate history. There is one genuinely dark detail worth preserving carefully within this correction so as not to overcorrect into a claim that is too simple in the opposite direction. Deep within certain craters near the moon's poles, particularly at the bottom of Shackleton crater near the South Pole, sunlight never reaches the floor at all, due to the extremely shallow angle at which sunlight strikes the polar regions. These permanently shadowed crater floors sit at temperatures as low as roughly 40 Kelvin, among the coldest natural locations found anywhere in the solar system. Scientists believe these permanently shadowed regions have trapped ancient water ice for billions of years, protected from evaporation by the constant and total absence of sunlight. This ice may eventually become an important resource for future lunar exploration and potential habitation. This is the one narrow and specific sense in which certain small regions of the moon truly are permanently dark, not an entire hemisphere. Just a handful of deep polar craters where geometry alone keeps sunlight out entirely. There is one more small detail worth including for anyone who has ever wondered about Earthshine. That faint glow, sometimes visible across the unlit portion of a crescent moon, This gentle glow comes from sunlight reflecting off Earth and softly illuminating the Moon's near side even during its darkest phase. The far side of the Moon never receives this reflected Earthshine at all, since it never faces our planet, meaning its true nights are subtly and genuinely darker than the nights experienced on the near side, even though both hemispheres receive the same direct sunlight overall. A small, legitimate exception worth holding onto within this larger correction. There is something tender about this particular myth once you sit with it fully. A beautiful piece of music, never actually claiming what generations of listeners assumed it claimed, and a genuine mystery hiding underneath the misunderstanding all along. Two hemispheres shaped by billions of years of separate geological history. Different not because of light and shadow, but because of the deep, patient forces that built them so differently in the first place. It is worth remembering too that no human being saw the far side of the Moon with their own eyes until spacecraft made it possible. For the entire span of human history, before 1959, every civilization that ever looked up at the night sky saw only the same familiar near side their ancestors had seen. The far side existed the whole time, cratered, ancient, utterly real, simply waiting quietly out of view until technology finally allowed us to turn around and look. You have now traveled from the depths of black holes through the birth of everything into the quiet corners of our own solar neighborhood. If you have made it this far into the night, let this be a natural place to rest for a moment before the journey continues deeper into the science and wonder still waiting ahead. Chapter 8. Mercury, not Venus, is Earth's closest neighbor. Here is a fact that tends to catch even lifelong space enthusiasts off guard. Ask almost anyone which planet sits closest to Earth, and you will get the same confident answer every time: Venus. It seems obvious. Venus orbits directly next to us. It is often called our sister planet, given how similar it is to Earth in size and mass. And for a long time, even textbooks and space agencies repeated this same answer without a second thought. But a careful recalculation published in 2019 revealed something genuinely surprising. The answer everyone assumed was correct turns out to depend entirely on what question you are actually asking. Let us start with what is definitely true. Venus really does make the closest approach to Earth of any planet in the solar system. When Venus passes directly between Earth and the Sun, the distance between the two planets can shrink to roughly 0.28 astronomical units, around 42 million kilometers, closer than any other planet ever gets to us. If closest simply means the shortest distance either planet has ever achieved at its nearest point, then Venus rightfully holds that title. But there is a very different question hiding underneath that one. Which planet is closest to Earth on average across the entire length of both orbits? Not just at the single closest moment, but averaged continuously over time. This turns out to be a meaningfully different calculation, and for decades, the standard method used to answer it was quietly flawed. The traditional approach many science educators used was simple. Subtract the average orbital radius of the inner planet from the average orbital radius of the outer planet. Earth sits at roughly 1 astronomical unit from the Sun. Venus sits at roughly 0.72 astronomical units. Subtract one from the other, and you get 0.28 astronomical units, the smallest gap of any planetary pair. It looks like solid math, but it quietly assumes something that is not actually true. It assumes Venus and Earth are always positioned on the same side of the Sun relative to one another. In reality, the two planets spend just as much time on opposite sides of the Sun as they do on the same side. In 2019, researchers named Tom Stockman, Gabriel Monroe, and Samuel Cordner published a detailed analysis in the journal Physics Today, addressing exactly this flaw. They developed something they called the point circle method, a more rigorous way of averaging distance across every possible position two orbiting bodies can occupy relative to one another. Rather than simply comparing average orbital radii, they also ran a direct simulation, tracking the positions of all 8 planets continuously across 10,000 simulated years, and recording which planet sat closest to Earth at each step along the way. The results overturned decades of casual assumption. Averaged properly across the full length of both orbits, Mercury turns out to be closer to Earth than Venus is. Roughly 1.04 astronomical units on average for Mercury, compared to roughly 1.14 to 1.18 astronomical units on average for Venus, depending on the exact method used. The reason comes down to orbital geometry. Venus spends significant stretches of time on the far side of the Sun from Earth. At those moments, the distance between the two planets swells to roughly 1.72 astronomical units, considerably farther than its closest approach ever gets. Mercury, by contrast, never strays far from the Sun at all given how tightly it orbits. This means Mercury also never strays terribly far from Earth. Even though it never achieves the same dramatically close approach Venus occasionally does, its distance from Earth stays comparatively steady and moderate far more consistently over time. The researchers confirmed their calculation with a running simulation covering 10,000 years of orbital motion, rather than relying on abstract formulas alone. Over that simulated stretch of time, Mercury sat closest to Earth roughly 47% of the time. Venus held that position roughly 36% of the time, and Mars claimed the remaining stretch at roughly 17%. Venus may win the single dramatic moment of closest approach, but across the full sweep of years, Mercury simply spends more total time being the nearer neighbor, a quiet, steady presence rather than an occasional dramatic one. Here is where the finding becomes genuinely delightful rather than merely technical. The same calculation reveals that Mercury is the closest average neighbor not just to Earth, but to every other planet in the entire solar system, including distant Neptune. Because Mercury hugs the Sun so tightly, it never travels terribly far from the gravitational center of the entire system. This keeps it moderately close to everything else orbiting that same center, even planets separated from it by enormous distances on paper. Researchers gave this broader pattern a memorable nickname, the whirly-dirly corollary. Borrowed from an episode of the animated series Rick and Morty, a playful piece of naming for a surprisingly elegant piece of orbital mechanics. It is worth being precise about what this finding does and does not change. The order of the planets outward from the Sun has not changed at all. Mercury remains the innermost planet exactly as it always has been. Venus still holds the record for the single closest approach any planet ever makes to Earth. Nothing about that specific fact has been overturned. What has changed is simply the answer to a different and more precisely defined question. Averaged honestly and continuously over time, Mercury turns out to be the planet that spends the most time near Earth, not Venus. This is also a genuinely recent recalculation, rather than something astronomers have always quietly known. The 2019 paper surprised much of the scientific community itself when it was first published. It is not settled textbook consensus dating back decades. It is a relatively new correction still working its way into common understanding. There is something delightful about carrying a fact like this forward. The kind of small, surprising truth you might find yourself repeating to someone else tomorrow simply because it feels too satisfying to keep to yourself. A planet often overlooked, small, scorched, rarely discussed with the same enthusiasm reserved for Mars or Venus, turns out to be quietly closer to you and to every other world in the solar system than anyone gave it credit for. It is worth remembering just how ordinary this misconception felt before the correction arrived. Nobody was being careless in any dramatic sense. Textbooks and popular science sites alike simply repeated a calculation that felt intuitively correct on its surface. This is exactly the same pattern that carried the Great Wall myth across 2 centuries. A reasonable seeming assumption repeated so often that no one thought to question the underlying arithmetic. The difference here is how quickly the correction spread once it was published. Within days, the 2019 paper had been shared across social media and covered by numerous science outlets. A rare case of a genuine correction to popular science, actually catching up with the misconception at real speed rather than lingering for generations. From the smallest planet in our solar system, let us shift focus entirely, away from the depths of space and back towards something much closer to home. The organ resting quietly behind your own eyes right now. Chapter 9. You already use all of your brain. For a moment, let us leave the depths of space entirely and turn our attention somewhere much closer, to the quiet organ resting behind your own eyes right now, working steadily even as you settle deeper into rest. You have almost certainly heard the claim before. Human beings only use 10% of their brain, the rest sitting dormant, unused, waiting for some hidden potential to be unlocked. It is a compelling idea. It has fueled entire films and countless motivational speeches, promising untapped genius waiting inside all of us. It is also completely false, and understanding why reveals something far more reassuring than the myth ever did. To trace where this idea began, we have to go back to a psychologist named William James, writing in 1907. James suggested that most people fail to make full use of their available mental resources, a reasonable observation about untapped potential and personal growth. Over the following decades, this general comment about psychological potential slowly transformed into something far more specific and far less accurate. A precise-sounding statistic claiming exactly 10% of brain activity was in use at any given time. No study ever actually produced this number. It emerged gradually through repetition, each retelling adding a little more false precision until an entirely invented statistic came to feel like an established scientific fact. Modern brain imaging technology has settled this question conclusively. Functional magnetic resonance imaging and positron emission tomography allow researchers to observe blood flow and activity across the entire brain in real time. These scans reveal activity distributed across virtually every region of the brain over the course of a single day, including during sleep. When the brain remains remarkably active, despite the body resting completely still, there are no permanently dark regions sitting unused, waiting quietly for some special circumstance to switch them on. Every part of the brain examined so far serves an active, identifiable function. Sleep itself offers one of the clearest pieces of evidence against the 10% myth. During the stage of sleep associated with vivid dreaming, known as rapid eye movement sleep, certain regions of the brain actually show activity levels comparable to full wakefulness. Meanwhile, during deeper stages of dreamless sleep, the brain remains busy, consolidating memories from the day, clearing away cellular waste products, and regulating hormones throughout the body. Far from powering down into some mostly dormant state, the sleeping brain remains a hive of coordinated activity, simply directed toward different tasks than the ones it handles while you are awake and reading or moving through your day. It is worth being precise about what these scans do and do not show, though. It is not accurate to say every single region fires simultaneously for every single task you perform. Different regions specialize in different functions. Visual processing happens primarily toward the back of the brain. Language processing draws heavily on regions typically found on the left side for most people. Movement and coordination rely on entirely different structures altogether. At any given moment, you are using the specific regions relevant to whatever you happen to be doing, reading these words, feeling the weight of a blanket, remembering something from earlier today. But across the full span of a day, nearly every region gets its turn. Nothing sits permanently idle the way the 10% myth suggests. There is also a compelling argument from evolutionary biology that makes the 10% myth even harder to accept once you consider it closely. The human brain is metabolically expensive, extraordinarily so. Weighing only around 2% of total body weight, the brain nonetheless consumes roughly 20% of the body's total energy at rest, a staggeringly disproportionate share of the body's resources dedicated to a single organ. Evolution operates under relentless pressure to eliminate waste. Traits and structures that consume significant energy without providing meaningful benefit tend to shrink or disappear entirely across generations. If 80 or 90% of the brain truly sat unused across the entire span of human evolutionary history, it is difficult to imagine evolutionary pressure allowing such an expensive organ to remain so wastefully oversized generation after generation. The sheer energy cost of the brain is itself powerful evidence that essentially all of it serves some genuine function. There is also clinical evidence worth considering here, drawn from cases of brain injury and damage documented across decades of medical practice. Damage to almost any region of the brain produces some noticeable effect on behavior, perception, or cognitive function. If large stretches of the brain genuinely sat unused, it would be reasonable to expect injuries to those regions to produce no meaningful symptoms at all. Yet, this is simply not what neurologists observe in practice. Even damage to comparatively small and specific regions can produce specific and often profound changes, affecting memory, speech, emotional regulation, movement, personality itself. This consistent pattern across countless documented cases strongly supports the conclusion that essentially the entire brain carries out meaningful active work. Nothing sits in genuine reserve waiting to be unlocked by some future breakthrough. Consider the case of Phineas Gage, a railroad worker from the 1840s whose survival after a severe brain injury became one of the most studied cases in the history of neuroscience. An iron rod passed directly through a specific region of his frontal lobe during a workplace accident. He survived, but those who knew him described significant changes to his personality and behavior afterward. This single case helped establish that specific brain regions govern specific aspects of who we are. Far from supporting the idea of vast unused reserves, this and countless similar cases documented since reveal a brain where nearly every region plays some meaningful, identifiable role in shaping thought, behavior, and identity. There is something quietly reassuring about this particular correction, different in tone from the myths busted earlier tonight. This is not a story about a hidden danger turning out to be harmless. It is a story about hidden potential turning out to already be fully present. You are not missing some locked away 90% of untapped genius waiting for a rare trigger to unlock it. You are already whole, already complete. Every part of the remarkable organ carrying you through this very moment already doing its quiet, necessary work. There is a gentle kind of peace available in that reframing, not the promise of hidden potential still waiting to be discovered somewhere inside you, but the recognition that everything you need has been present and working all along. Perhaps the most valuable lesson from this particular myth has less to do with neuroscience and more to do with how appealing a false promise can be. The idea of hidden, untapped potential is seductive precisely because it suggests an easy shortcut, some dormant switch waiting to transform an ordinary mind into something extraordinary. The truth offers something quieter, but ultimately more solid. Growth and improvement remain entirely possible, not by activating unused brain tissue, but through practice, rest, learning, and the ordinary patient work of strengthening connections that are already fully active within a brain that was never missing anything to begin with. From the workings of your own mind, let us travel back outward once more, toward a region of space long imagined as chaotic and crowded, a region that turns out to be almost entirely the opposite. Chapter 10. The asteroid belt is almost entirely empty. Close your eyes and picture a spacecraft threading its way through the asteroid belt. Chances are the image that comes to mind involves tumbling boulders, narrow gaps, a pilot weaving frantically between rocks the size of buildings. This image comes almost entirely from popular science fiction. The Millennium Falcon dodging asteroids in dramatic close calls remains one of the most iconic space sequences ever filmed. The problem is that this vision of the asteroid belt is almost the exact opposite of reality. The asteroid belt is not a crowded, dangerous obstacle course at all. It is one of the emptiest regions human spacecraft regularly travel through. To understand just how empty, consider the sheer number of spacecraft that have already crossed it without a single collision. Pioneer 10 and 11, Voyager 1 and 2, Galileo, Cassini, New Horizons, Juno. A dozen or more missions spanning decades of spaceflight have passed directly through the belt on their way to the outer solar system. Not one of them has ever suffered a collision with an asteroid. Mission planners do not even bother designing special evasive maneuvers to dodge asteroids along the way. The odds of a meaningful collision are estimated at below 1 in a billion for any given crossing. Some of these missions have even used the opportunity presented by the belt to conduct close flybys of individual asteroids for scientific study, rather than treating the region as a hazard to survive. The Dawn spacecraft spent time orbiting both Vesta and Ceres directly, two of the largest bodies within the belt, gathering detailed imagery and data without any of the danger popular imagination might suggest. Far from a gauntlet to be nervously navigated, the belt has become something closer to a scientific destination in its own right, calm enough for a spacecraft to slow down deliberately and linger in orbit around individual objects for extended study. So why does the popular image diverge so dramatically from reality? The answer comes down to scale, a concept that becomes almost impossible to intuitively grasp once you consider the true size of the region involved. The asteroid belt stretches across a region of space roughly 150 million kilometers wide, positioned between the orbits of Mars and Jupiter. Despite containing millions of individual objects ranging from tiny pebbles to the dwarf planet Ceres, the total combined mass of everything in the belt adds up to less than 4% of the mass of Earth's own moon. Spread across such an enormous volume of space, that minuscule total mass translates into typical distances between sizable asteroids measured in the hundreds of thousands of kilometers, far greater than the distance separating Earth from its own moon in many cases. It helps to try to picture this scale directly, rather than simply hear the numbers described. If you were standing on one asteroid somewhere within the belt, the nearest neighboring asteroid of comparable size would likely be too far away to even see clearly with the naked eye, let alone pose any immediate collision risk. The romantic vision of ducking and weaving between tumbling rocks in rapid succession simply does not match the reality of traveling through a region this vast and this sparse. A spacecraft crossing the belt experiences something closer to traveling through profound emptiness, punctuated by exceedingly rare and distant specks of rock. Consider the scale another way. If every asteroid in the belt, larger than about 100 meters across, were shrunk down to the size of a grain of sand, the entire collection would still be scattered across a volume roughly comparable to a large sports stadium, with only a small handful of grains present at any given moment. This is the true character of the region, not a crowded field of tumbling debris, but a vast, mostly empty volume containing a comparatively tiny amount of scattered material drifting slowly along well-understood and thoroughly mapped orbital paths. This raises a natural question about how the asteroid belt formed in the first place, given how sparse it actually is today. Early in the solar system's history, the region between Mars and Jupiter likely contained enough material to form a proper planet. But Jupiter's immense gravity continuously disrupted the orbits of the material in this region, preventing smaller bodies from ever gently merging together the way planets elsewhere in the solar system managed to form. Instead of coalescing into a single world, the material remained scattered and fragmented, occasionally colliding and breaking apart rather than combining and growing, leaving behind the sparse, scattered field of debris we observe today rather than a proper fifth rocky planet. There is an important distinction worth drawing clearly here, since a very different structure elsewhere in the solar system can easily be confused with this one. Saturn's rings represent something almost entirely opposite from the asteroid belt, despite both being popularly imagined as crowded fields of rock and ice. Saturn's rings are extraordinarily thin, often no more than about 10 meters in vertical thickness, despite spanning a diameter of hundreds of thousands of kilometers. And within that thin disk, particles are packed together far more densely than anything found in the asteroid belt. The asteroid belt spreads modest total mass across an enormous three-dimensional volume. Saturn's rings concentrate significant mass into an extremely thin, flat plane. Two very different structures that popular imagination sometimes blurs together despite their genuinely different characters. There is a particular kind of pleasure in this correction, not relief from fear exactly, more a kind of gentle deflation of a beloved cinematic image, followed by something arguably more impressive in its place. The true asteroid belt does not offer white-knuckle tension and narrow escapes. It offers something closer to profound, quiet vastness. Millions of scattered fragments drifting through emptiness so complete that spacecraft simply glide through without incident, decade after decade, mission after mission. There is something worth sitting with in that image. Real emptiness on a scale so enormous it makes even a densely populated seeming region of our own solar system feel almost entirely silent and still. It is worth remembering that filmmakers are not simply careless when they invent a crowded, dangerous asteroid belt for the screen. Genuine emptiness rarely photographs well. A ship gliding calmly through open space for several uneventful minutes does not generate the tension a story requires. So writers reach for drama, tumbling rocks, narrow escapes, because those images serve the story even though they misrepresent the science. Understanding this pattern helps explain why so many space myths persist so stubbornly, not because anyone intends to deceive, but because compelling fiction and accurate science do not always pull in the same direction. From this sparse, scattered field of ancient debris, let us travel outward to something almost the opposite in character. A ring system dense enough to be seen clearly through a small telescope from Earth, and yet fragile enough that it may not last much longer at all on a cosmic timescale. Chapter 11. Saturn's rings are young and already vanishing. Saturn's rings are perhaps the single most recognizable feature in the entire solar system. A thin, brilliant halo of ice and rock circling a golden planet, instantly identifiable even to people who have never studied astronomy at all. For most of human history, these rings were assumed to be as old and permanent as the planet itself, a fixed, unchanging feature that had always existed and always would. Recent research tells a very different and far more delicate story. Saturn's rings may be remarkably young by cosmic standards, and they are actively disappearing at a pace scientists can now measure directly. The process driving this disappearance has been given a fittingly poetic name: ring rain. Saturn's powerful magnetic field interacts continuously with the icy particles that make up its rings. Tiny fragments of ice become electrically charged through exposure to ultraviolet light from the sun or through collisions with microscopic dust grains. Once charged, these particles begin to feel the pull of Saturn's magnetic field lines, which curve inward toward the planet's upper atmosphere. Gravity then draws these charged particles down along those magnetic field lines, where they vaporize upon entering Saturn's atmosphere, effectively raining down onto the planet as water and reacting chemically with the gases already present there. Researchers led by NASA scientist James O'Donoghue have estimated the rate of this process with startling precision. Their measurements suggest that ring rain drains enough water from Saturn's rings to fill an entire Olympic-sized swimming pool roughly every 30 minutes. This may sound like a small amount relative to the enormous total mass of the rings, but sustained continuously over millions of years, the effect compounds into something genuinely significant. The discovery of ring rain did not arrive suddenly. It emerged gradually from decades of accumulated clues that initially seemed unrelated. Voyager spacecraft flying past Saturn in the early 1980s detected strange variations in the planet's ionosphere, along with unexplained density patterns within the rings themselves. At the time, researchers were not certain what connected these separate observations. It took decades of further study using ground-based telescopes in Hawaii, along with data gathered directly by the Cassini spacecraft, to finally assemble the full picture. Charged icy particles raining down along magnetic field lines, slowly but steadily eroding the rings from within. Based on this ring rain rate alone, researchers calculated that Saturn's entire ring system would completely disappear within roughly 300 million years. But ring rain is not the only mechanism draining material from the rings. Data gathered by the Cassini spacecraft during its final dramatic dive into Saturn's atmosphere revealed an additional stream of ring material falling directly into the planet's equatorial region, separate from the polar ring rain process. Combining both of these loss mechanisms together shortens the estimated remaining lifetime of the rings considerably. Some estimates suggest the rings may have less than 100 million years left. Others, drawing on 2023 studies published in the journal Science Advances, suggest a wider range of somewhere between 15 million and 400 million years remaining. Compared to Saturn's own age of roughly 4.5 billion years, any of these estimates represent a strikingly brief remaining lifespan, a geological blink of an eye relative to the age of the planet the rings surround. This naturally raises a fascinating question. If the rings are disappearing this quickly, how old are they in the first place? Data gathered during the Cassini mission's final years suggested the rings themselves may be surprisingly young, possibly no more than somewhere between 10 million and 400 million years old. This stands in stark contrast to Saturn's own age of 4.5 billion years. If these estimates hold up, the rings would represent a relatively recent addition to Saturn's appearance, forming long after the planet itself had already existed for most of its current lifetime. It is worth being honest about the uncertainty still surrounding this question, though. A minority of researchers continue to argue the rings could be considerably older than these newer estimates suggest. This remains a genuinely active area of ongoing planetary science rather than a fully settled conclusion. Where would rings this substantial have come from if Saturn did not form with them originally? Leading theories suggest the rings may have originated from the destruction of an icy moon, perhaps one that wandered too close to Saturn and was torn apart by powerful tidal forces, or one that collided catastrophically with another orbiting body. The debris from such a destructive event would have spread out into the thin orbiting disk we now recognize as Saturn's rings, a genuinely violent origin story hiding behind what appears from Earth as one of the most serene and beautiful sights in the entire solar system. There is a particular kind of bittersweet wonder worth sitting with here. Researchers studying this phenomenon have been remarkably candid about what it means for us as observers. As James O'Donoghue himself has put it, we may simply be fortunate to exist during the narrow window when Saturn happens to display such a magnificent ring system at all. Consider that Jupiter, Uranus, and Neptune all possess only faint fragmentary ring systems today. It is entirely possible these planets once hosted rings just as spectacular as Saturn's current display, long before human beings existed to witness them. If ring systems are genuinely temporary features rather than permanent fixtures, we may simply have arrived at exactly the right moment in cosmic history to catch Saturn mid-performance. A performance that began relatively recently and will eventually end, long before Saturn itself ever will. Let this thought settle gently rather than land as something frightening. Nothing about this timeline threatens anyone alive today or countless future generations to come. Millions of years remain ahead regardless of which estimate proves most accurate. Instead, let it deepen your appreciation for something you may have always assumed would simply always be there. A quiet reminder that even features as vast and beautiful as planetary rings exist within their own span of time, beginning, enduring for a while, and eventually fading, just as so much else in the universe does. There is a certain generosity in how researchers themselves have chosen to frame this finding. Rather than treating a temporary ring system as a loss to mourn in advance, they consistently describe it as a rare privilege currently being enjoyed. Future generations of astronomers thousands of years from now may study a Saturn with noticeably thinner rings than the ones visible through telescopes tonight, and eventually, far into the future, a Saturn with no rings at all. Knowing this does not diminish the beauty of what can be seen right now. If anything, it sharpens it. A reminder that witnessing something rare and temporary is itself a kind of quiet privilege worth appreciating fully in the moment it is offered. From a ring system slowly dissolving into its host planet, let us return once more to the object that opened this entire journey. Except this time, we will look at it from the other end of its own impossibly long life. Chapter 12. Black holes are not forever. We began this journey tonight with black holes, correcting the image of a hungry predator into something far calmer and more governed by ordinary physics. Now, near the close of this episode, we return to the same object one final time, and what we find waiting there may be the most peaceful correction of the entire night. Even the darkest, most feared object in the known universe turns out to be temporary. This idea traces back to a groundbreaking discovery made in 1974 by physicist Stephen Hawking. At the time, most physicists assumed black holes were truly eternal, objects so powerful that absolutely nothing, including light, could ever escape their pull. Once formed, a black hole would simply exist forever, unchanging. Hawking approached the problem by combining general relativity, which governs gravity on a large scale, with quantum mechanics, which governs the strange probabilistic behavior of particles on a tiny scale. What he found overturned the assumption of permanence entirely. Quantum mechanics tells us that empty space is never truly empty. Even a genuine vacuum constantly generates and reabsorbs pairs of particles and their corresponding antiparticles, existing only for the briefest possible instant before vanishing again. Hawking realized that near the boundary of a black hole's event horizon, something remarkable could happen to this ordinary quantum process. Occasionally, one particle from such a pair falls into the black hole, while its partner escapes outward into surrounding space. From the perspective of a distant observer, this looks exactly like the black hole itself, emitting a faint stream of particles. This theoretical emission has since become known as Hawking radiation in his honor. Quantum mechanics tells us that empty space is never truly empty. Even a genuine vacuum constantly generates and reabsorbs pairs of particles and their corresponding antiparticles, existing only for the briefest possible instant before vanishing again. Hawking realized that near the boundary of a black hole's event horizon, something remarkable could happen to this ordinary quantum process. Occasionally, one particle from such a pair falls into the black hole, while its partner escapes outward into surrounding space. From the perspective of a distant observer, this looks exactly like the black hole itself, emitting a faint stream of particles. This theoretical emission has since become known as Hawking radiation in his honor. It helps to picture this process as a kind of cosmic bookkeeping happening at the very edge of the black hole's boundary. Every pair of particles that briefly flickers into existence represents a tiny loan borrowed from the surrounding vacuum, normally repaid instantly as the pair recombines and vanishes. But right at the event horizon that repayment sometimes cannot happen, one partner crosses the boundary permanently while the other escapes carrying real energy outward. The universe balances its books by drawing that energy from the black hole itself, ever so slightly, reducing its mass with each such event. Repeated over unimaginable stretches of time, this slow, steady bookkeeping eventually adds up to something significant. The consequence of this process is genuinely profound. Emitting this radiation causes a black hole to lose a tiny amount of mass over time. Since mass and gravity are directly connected, this means a black hole is very slowly and very gradually shrinking, losing energy back into the surrounding universe rather than holding everything captive forever. Given enough time, this process would eventually cause a black hole to evaporate away entirely, ending its existence not with a dramatic collapse, but with a slow, patient dissolution stretched across almost incomprehensible spans of time. It is important to be honest and precise about the timescales involved here, since they are almost impossible to hold meaningfully in the human mind. A black hole with roughly the mass of our own Sun would take on the order of 10 to the power of 67 years to fully evaporate through this process. To offer some sense of scale, the current age of the entire universe is only about 14 billion years. The evaporation timescale for even a relatively small black hole dwarfs the current age of the universe by a margin so enormous it defies ordinary comparison. Supermassive black holes sitting at the centers of galaxies would take vastly longer still given their far greater mass. Numbers so large, they exist primarily as mathematical abstractions rather than anything resembling a practical countdown. It is also worth being transparent about the current scientific status of this theory. Hawking radiation remains, theoretically, well-grounded, built on rigorous mathematics combining two of the most successful frameworks in all of physics. However, it has never been directly observed. The radiation involved is predicted to be so extraordinarily faint that detecting it directly remains far beyond the capability of any instrument currently available to science. This does not mean the theory is in serious doubt among physicists. It remains one of the most widely accepted predictions in theoretical physics today. But intellectual honesty requires acknowledging that direct observational confirmation has not yet arrived. Some researchers have attempted to find indirect analogues of this process in laboratory settings here on Earth. Using specially arranged systems involving sound waves in fluids or light waves in specially engineered materials, scientists have created what are sometimes called analog event horizons. These experiments have produced results consistent with the basic mathematics underlying Hawking radiation, offering encouraging indirect support for the theory even without observing an actual astrophysical black hole doing the emitting. It remains a genuinely active and creative area of physics. Researchers approaching an almost unobservable prediction from as many clever indirect angles as they can devise. There is something quietly moving about how this chapter completes the arc that began this entire episode. The object introduced in dread, as a predator waiting silently in the darkness, turns out by the end of this journey to be patient rather than hungry, temporary rather than eternal. Even the most extreme concentration of gravity the universe has ever produced eventually gives its energy back, returning matter to the wider cosmos across timescales too vast for any of us to ever witness directly, but real nonetheless. Nothing in the universe stands truly apart from everything else. Not even a black hole. Everything eventually rejoins the larger story unfolding around it, given enough patience and enough time. Consider what this means for the very last black holes that will ever exist in the universe. Long after every star has burned out and every galaxy has drifted apart. In the almost unimaginably distant future, long after this episode, any listener, and indeed any civilization, has faded into memory, the last remaining black holes will still be quietly emitting their final faint traces of radiation, shrinking gradually toward nothing at all. Some physicists consider this one of the final acts in the long story of the universe itself, a slow, patient release of the very last concentrated remnants of matter and energy back into an increasingly cold and empty cosmos. Even in that far future darkness, nothing remains sealed away forever. If even the darkest object in existence eventually dissolves gently back into the universe around it, perhaps it is worth asking a deeper question still. Where exactly did all of this begin? And does the universe even have a center to call its own at all? Chapter 13. The universe has no center, and you are standing in it. Earlier tonight, we corrected the image of the Big Bang as an explosion into empty waiting space. We learned instead that it was an expansion of space itself, happening everywhere at once rather than at any single point. Now let us follow that correction all the way to its natural and rather beautiful conclusion. If the universe expanded from everywhere at once, then the universe has no center at all. And in a very real sense, you are standing exactly as close to its center as anywhere else in all of existence. Let us begin with the question almost everyone eventually asks once they first hear about the Big Bang: where did it happen? It feels like a reasonable question. Every explosion we experience in daily life has an origin point, a location you could walk toward and eventually stand at the exact center of. But this question quietly assumes something about the nature of the Big Bang that simply is not true. It assumes there was empty space already existing, waiting for an explosion to occur somewhere within it. As we already established, there was no such pre-existing empty space. Space itself came into being through this event, which means asking where it happened is a bit like asking, what is north of the North Pole? The question assumes a structure that does not actually exist. Here is a way to make this concept feel more concrete rather than purely abstract. The extremely hot, dense state that existed at the very beginning was not a small object sitting somewhere within a larger, empty universe. It was everywhere that exists, compressed into an extraordinarily small volume relative to what it would later become. Every single point in today's vast universe, including the exact spot where you are lying right now, traces back through cosmic history to a location that was part of that original hot, dense state. This means every point in the universe has an equally legitimate claim to having been present at the beginning. Not one privileged center surrounded by empty space that came later, but an entire universe of equally valid starting points, all of them still connected to that same origin through an unbroken chain of expansion stretching across billions of years. Here is a way to make this concept feel more concrete rather than purely abstract. The extremely hot, dense state that existed at the very beginning was not a small object sitting somewhere within a larger, empty universe. It was everywhere that exists, compressed into an extraordinarily small volume relative to what it would later become. Every single point in today's vast universe, including the exact spot where you are lying right now, traces back through cosmic history to a location that was part of that original hot, dense state. This means every point in the universe has an equally legitimate claim to having been present at the beginning. Not one privileged center surrounded by empty space that came later, but an entire universe of equally valid starting points, all of them still connected to that same origin through an unbroken chain of expansion stretching across billions of years. It can help to imagine reversing the expansion in your mind, running the entire history of the universe backward like a film played in reverse. As you rewind, every galaxy would appear to rush back together, space itself contracting steadily rather than any individual object flying inward. Eventually, as you continued rewinding far enough, every point you can currently observe would converge into an extraordinarily dense state alongside every other point in the observable universe. Not because they traveled towards some distant central location, but because the space separating them was itself shrinking uniformly everywhere at once. This concept connects directly back to the balloon analogy introduced earlier tonight. Picture again those dots painted across the surface of an expanding balloon. As the balloon inflates, every dot moves away from every other dot simultaneously. Crucially, no dot sits at the center of the balloon's surface itself. The surface has no center at all when considered purely as a two-dimensional space wrapped around the balloon. Our universe behaves in a directly analogous way, though extended into 3 dimensions of space rather than the two-dimensional surface of a balloon. Every galaxy observes every other galaxy moving away from it, and every galaxy would be equally correct in concluding that the expansion appears centered on its own location, because in the relevant sense, it genuinely is. This property of the universe has a formal name in cosmology, homogeneity and isotropy. Homogeneity means the universe looks roughly the same everywhere you examine it at a sufficiently large scale. Isotropy means the universe looks roughly the same in every direction you look from any given point. Together, these two properties describe a universe with no privileged location and no privileged direction. A universe where the view from any sufficiently distant vantage point would look remarkably similar to the view from any other. Extensive observational evidence, collected over decades, strongly supports both of these properties, holding true at the largest scales astronomers can measure. Even Albert Einstein himself initially resisted the implications of his own equations when they first suggested an expanding universe rather than a static, unchanging one. He famously introduced an additional term into his equations, specifically to force a static solution, later calling this decision his greatest blunder once observational evidence from astronomer Edwin Hubble confirmed that the universe was indeed expanding after all. Even one of the greatest scientific minds in history needed time and evidence to accept just how strange and counterintuitive this particular cosmic truth really is. It is worth being precise about one remaining area of genuine scientific uncertainty here. Current measurements strongly favor a universe that is very close to geometrically flat on the largest observable scales. However, this remains an active area of precision cosmology. Small deviations from perfect flatness remain possible and continue to be investigated using increasingly sophisticated observational techniques. The broader conclusion about there being no center or privileged location within the universe does not depend on resolving this remaining question. It holds true regardless of the precise underlying geometry involved. Sit with this idea for a moment and let it fully land. You are not living in some ordinary, unremarkable corner of a vast universe centered somewhere far away from you. There is no faraway center. There never was. Wherever you are lying right now, as you listen to this, is exactly as central to the universe as any other location that has ever existed or ever will exist. This is not a small comfort offered gently at the end of a long night. It is a literal cosmological fact. verified through decades of careful observation and mathematics. You occupy a position of genuine cosmic centrality, simply because every position does. There is a strange vertigo to first absorbing this idea, followed by something closer to belonging once it settles. Human history is full of moments where we assumed ourselves to occupy a special, privileged position in the universe, only to discover otherwise. Earth was once assumed to sit at the center of everything, until careful observation proved the sun held that role instead. And later still, that the sun itself was merely one ordinary star drifting through the outer reaches of one ordinary galaxy among countless billions. This latest correction feels different though. Rather than removing us further from any special status, it restores something quietly profound. Not a single unique center that only one location can claim, but a universe generous enough that every single point within it shares equally in that same cosmic centrality, including exactly where you are right now. Everything you have learned tonight now converges toward a single closing thought. 13 corrections. 13 small pieces of misplaced human intuition gently set right. Chapter 14. Closing meditation, built from corrected mistakes. 13 corrections now rest gently behind you. No new facts remain to be introduced from here. Only a slow, quiet gathering together of everything this night has offered you. Notice something these 13 corrections all share in common. Each one began the same way, a piece of everyday human intuition, reasonable, comfortable, built from a lifetime of ordinary experience here on Earth. Explosions have centers, so surely the birth of the universe must have had one too. Vacuums pull things toward hungry emptiness, so surely a black hole must hunt the same way. Cold is simply the absence of warmth, so surely the vastness of space must be the coldest place imaginable. Each of these intuitions served you well here on Earth. None of them were foolish to hold. They simply were never built to stretch across the scale of galaxies, across billions of years, across distances too vast for any human mind to have evolved an intuition for in the first place. There is no failure hiding anywhere in any of these corrected mistakes. Every one of them was simply the ordinary furniture of a mind built for a much smaller and much closer scale of experience. A mind built to judge distance across a savanna, to judge temperature across a single season, to judge danger across the reach of an arm rather than the reach of a light year. That the universe occasionally surprises a mind built this way is not a flaw in you. It is simply the natural gap between a nervous system shaped by evolution here on Earth and a cosmos that never once consulted that nervous system while arranging itself. Let your body settle a little deeper now. You began this night believing the universe hunted, that it exploded violently into being, that it would freeze you instantly given the chance. You now know something gentler, a universe that behaves according to quiet, patient laws, consistent everywhere, indifferent to fear, governed by geometry and time rather than malice or hunger. You learned that the sun you have watched your entire life is more brilliant than you ever gave it credit for, that the silence surrounding nearly everything in existence is deeper and more complete than any silence you will ever encounter here at home, that a wall built by human hands centuries ago remains humble enough to hide even from orbit, that the moon keeps no true darkness from you at all beyond a handful of quiet frozen craters near its pole. You learned that a small, overlooked planet has been quietly closer to you than anyone ever gave it credit for, that your own mind was never missing some hidden reserve of untapped potential, that you have always been whole, already complete, that a belt once imagined as crowded and dangerous turns out to be one of the emptiest places human spacecraft have ever safely crossed. You learned that Saturn's rings, that impossibly beautiful halo circling a golden world, are young and fading, and that you happen to be alive during the narrow, fortunate window when they can still be seen at all. You learned that even a black hole, the very object that opened this entire journey in dread, is patient rather than eternal, slowly returning its own darkness back to the light of the wider universe across spans of time too vast to truly picture. You learned, too, that the universe itself began everywhere at once, silently, without any single point to trace it back to, and that this same absence of a center extends outward into everything you have ever looked up at. No privileged place, no forgotten corner, only an endless field of equally valid centers stretching in every direction as far as any telescope has ever managed to see. And now, the final correction, the one holding all the others gently together. There is no center to the universe, which means there never was a faraway place more important than the one you occupy right now. You are not small, not separate, not distant from any of this. You are built from the same stretching fabric of space that has been quietly expanding since the very beginning. The atoms resting in your body were forged inside stars that lived and died long before the sun itself ever formed. The same silence that fills nearly the entire universe surrounds you gently right now. The same patient physics governing black holes and dying rings and distant silent nebulae governs the quiet rhythm of your own breathing, right now, in this room. There is a kind of gentle circularity in ending here. Every atom of carbon and oxygen and iron carried inside you tonight was assembled inside the heart of some ancient star long before Earth itself ever existed, scattered outward across the galaxy when that star finally ended its own long life, gathered slowly over billions of years into the dust that eventually formed this planet and eventually formed you. You are not a visitor observing the universe from some separate vantage point outside of it. You are the universe, arranged for a little while into a shape capable of wondering about itself, resting quietly tonight, listening to its own story being gently retold. Let every correction from tonight settle over you like a blanket rather than a lesson. A universe stranger than you were ever taught, gentler than you were ever warned, centerless, silent, patient, slowly dissolving black holes and vanishing rings and all. Picture it now one final time. Earth quietly turning below you, the moon holding its far side in permanent privacy just beyond view, Saturn circled by a halo that will not last forever but is here tonight regardless. Farther still, a black hole, ancient, patient, slowly giving its own darkness back to the light. And farther still than that, the very edge of everything you can observe, silent, centerless, endless. There is nowhere else you need to be. There is nothing else you need to understand tonight. You are exactly where the universe intended anyone to ever be, which is to say, everywhere, all at once, including here. Let the corrections you carried into this room tonight simply rest beside you now. No longer facts to remember, only a quieter, softer way of seeing the same sky you have always looked up at. A sky that never truly hunted you, never truly exploded into being, never truly promised to freeze you the moment you stepped beyond it. A sky with no center anywhere within it, which means it has never once excluded you from its very middle. Rest now. The universe already has